welcome to the Daily Space for June 7th, 2018. As always, I am your host, Dr. Pamela Gay, and today I'm going to take you on a fast-paced journey through, well, a lot of what's new in astronomy and space science. Now, I'm realizing I don't actually have the chat up at a size I can read, so pardon me for a moment while I open the correct windows. So my plan for today is, it's been an incredible news week. We have had news coming in from the American Astronomical Society meeting out in Denver, Colorado. And with all that news, has also come all the regular stuff that just keeps on happening as we keep on exploring. So we've had extra news due to the meeting, and we have had just all the regular discoveries coming out of NASA and so many other organizations. So without further ado, with further ado, at the conclusion of today's extra long episode of the Daily Space, we're actually going to transition over, and I'm going to bring you coverage of NASA's press conference on new results coming from the Mars Curiosity rover. No one quite knows what's going on, but we know that the results are getting published today in the journal Science, and that they're exciting enough that NASA decided they needed to go out on the internet live. Okay, so let's switch on over to today's first news story, which comes to us from NASA and concerns the Juno space probe. This little mission that has a few problems where it can't quite. Specifically, this little spacecraft has been having issues with its engines. And right now, it's in really short orbits going around and around Jupiter. What they're looking to do is to transition from orbiting Jupiter every 14 days to instead orbiting Jupiter every 53 days. This will be a little bit easier on all of the systems on board, but with this prolonged time to get round and round the great planet, in order for them to accomplish the science they want to do with Juno, they have to expand how long Juno is going to be funded to orbit Jupiter. Basically, the science takes the number of orbits it takes. If those orbits go from 14 days to, 53 days, it's going to take a larger number of months to accomplish all of the science. So, NASA, thanks to funding also from Congress, has been able to add to the Juno mission an additional 41 months of funding. So this spacecraft is going to keep on bringing us amazing data for many more months and years than we'd previously hoped for. Now, part of what this spacecraft has been able to do is help us better understand the lightning strikes that take place in the atmosphere of Jupiter. Here on our own planet Earth, we see lightning strikes on a regular basis, and they're predominantly in the equatorial and mid-latitude regions. So here where I am in Tornado Alley, USA, we get lightning on, some months of the year on a daily basis. But if I keep traveling north and visit friends up in Canada, there's going to be a lot less lightning. And the further north I get, the less lightning I'll see. Same thing works in the southern hemisphere. Now on Jupiter, it turns out that most of the lightning actually takes place in the polar regions. And this difference in location has been one of those great mysteries that really make, planetary scientists scratch their heads. And it took an argument of thermodynamics to work this out. Here on the Earth, our lightning is driven by massive temperature variations, driven by heating that occurs in excess at the equator and the mixing of cold air that's coming in on fronts either from the north in the northern latitude or coming up from the south in the southern latitudes. This mixing of moist hot air and changing temperatures, it generates storms, powerful storms that, well, shoot lightning. Jupiter, it has a slightly different circumstance. With Jupiter, this world actually has a lot of internal heat. It's big, its internal self-gravity is driving internal temperatures to rise. That rising heat rises all across the world. Now, Jupiter is about 5 times further from the sun than we are. This means that it gets about 25 times less light from the sun than we do. This works out to less heating. As it turns out, at the equatorial regions of Jupiter, the heat coming from the outside, from the sun, is able to balance out the heat on the inside, driven by Jupiter's, gravitational compression and all the heat that comes from that. This makes the equatorial regions more, atmospherically stable. As you move up towards the poles, or down, up towards the northern pole, down towards the southern pole, as you move towards those poles, the planet is getting less and less light, less and less heat from the sun. This means that you end up with a thermodynamic instability between the rising heat that's generated inside the planet and the cool temperatures that exist naturally at the surface of the planet. These storms, driven by the internal heating of this world, generate massive amounts of lightning in the polar regions on Jupiter. So in both cases, we have thermodynamic instabilities that are driving storms. But because of the differences in where you get the greatest difference in heating on our two worlds, these storms occur in very different places. Again, this is just another result coming to us from the Juno spacecraft. Now, moving much further out in our universe, we have a story of stellar collisions. This particular story is about what happens during galaxy mergers. Galaxies in general, if they have a sphere, if they aren't just a plain old plane of stars like we see with some, planar sombrero-ish looking galaxies. The sombrero has a disk of stars. That was a bad example that came out of my mouth. When we see edge-on galaxies that are just an edge and have no bulge in the center, those appear to not have supermassive black holes. But as we add bulges, we also add supermassive black holes that have a mass that is fairly well related to that bulge's size. Now, when two different galaxies collide, such as we see here in this image of NGC 2623, these systems have two supermassive black holes, and the act of colliding drives material in the galaxies to migrate in towards the center of the galaxies. New research coming to us from the University of Colorado Boulder discusses how it is that different kinds of merging galaxies can light up the accretion disks surrounding these supermassive black holes, creating what we call active galactic nuclei. This group of researchers, led by Scott Barrows, indicates that in some cases, you actually only end up with one of these two supermassive black holes becoming active. And these variations in, is it one of them, is it both of them, is related directly to what is the size difference between these two colliding systems. If you have a puny system falling in, you're going to have a very different outcome than if you have two equally sized and two large sized systems colliding together. The activation seems to occur most often when galaxies are mismatched. So this means that when you have a small galaxy falling into a large galaxy, you are more likely to only see one of the two black holes get inundated with gas and dust and light up as active galactic nuclei. I'm just going to explain one more time, though. It's not the black hole lighting up. Black holes do not emit light. There is a disk of material that is streaming around the black hole, and it's material feeding into that disk, getting it hot and thick, that causes the light to be generated. So we now have one new thing to go ahead and look for. They have so far been using the Chandra X-ray Observatory to look deep into the centers of merging systems and identify exactly where we do and don't have activity. This is just a cool little result with pretty pictures, so I decided to bring it to you. Now, moving on and continuing our study of galaxies. One of the things that we've been struggling to try and figure out is how much our own galaxy weighs. Well, weight is probably the wrong word. How much mass is in our galaxy? Trying to figure this out isn't as easy as we would like, and over the past decade or so, we have adjusted our estimates of our galaxy's mass up and down in various ways. Using a new idea, theorists and observers are now joining forces to look at how it is dwarf galaxies move around our galaxy as they get cannibalized by the Milky Way's gravity. In this artist's rendition, we see the tidal streams of disrupted dwarf galaxies. As the stars that we're observing reach greater and greater distances from the center of our galaxy, we are able to estimate how much mass is located inside these single stars' orbits by knowing how fast these stars are orbiting around the Milky Way, and by being able that's all there is. By knowing how fast these stars are going around our Milky Way, we have the potential to directly measure our Milky Way's mass, because the star's individual mass is minuscule compared to the mass of the Milky Way, and the equations work out that all that really matters is the mass of the Milky Way. Now, trying to get at the exact orbital velocity of any one star at that great of a distance is a bit of a struggle. So instead, what we're looking at is the overall trends in how it is that all of these different galaxies are getting shredded. And these aren't just helping us weigh the stuff we know about in our Milky Way. It isn't just telling us the mass of the stars and the gas. It's also telling us the amount of mass in the Milky Way that is tied up in dark matter. We're able to actually get down at details such as how much dark matter is located between one dwarf galaxy's tidal stream and another dwarf galaxy's tidal stream. This is helping us understand the distribution of the dark matter and the mass of our own galaxy, including both the stuff we can see and the stuff we can't. Now, what's kind of frustrating is the scientists, in discussing this, do use the word weight over and over. One thing I want to remind you of is weight and mass are directly related. The amount of gravity that one thing exerts on another is due to how many atoms are in it, how much mass it has, according to the coupling between Higgs bosons and those particles that make that stuff up. Weight is how much that mass is being interacted with gravitationally. So your weight is a measure of how the Earth is pulling on your mass. if you go to the surface of the moon, you will have the exact same mass, unless, of course, space sickness causes you to lose a good deal of your atoms. But unless something like that happens, you're going to have the same mass on the Earth and on the moon. But because the moon has a lot less gravity, you will perceive yourself as weighing less. Your knees will feel less stress, and instead of walking, you will bounce across the lunar surface. So be careful with your words, journalists, and be careful with your words, people who are writing press releases. What we're weighing is not actually a thing. What we're measuring is the mass of the Milky Way. Now, moving on to another galaxy-related story. What we have here is an attempt to understand. Sorry, I'm trying to find the press release this is related to. What we're trying to understand is how stars are and aren't formed in dwarf galaxies, and how these dwarf galaxies have over time built up new massive galaxies. Now, what we have in this image is a computer simulation of a variety of small early blobs of material that formed stars and gravitationally interacted to eventually merge in with a bigger galaxy. This is a simulation. It isn't actually an image. This particular simulation of a bunch of satellite galaxies is designed to help us get a handle on the gas densities throughout this system. So red corresponds to an extremely dense area of gas and dust. Blue is a much lower density of gas and dust, and black means there's nothing there. Now, what they're trying to do is get a handle on how exactly things would have formed and where exactly we should go looking to find the first stars that formed. As these systems came together gravitationally, initially they were nothing but gas and dust. Then, in the highest density initial regions, we had star formation. As these systems interacted over time, the gas and the dust interacted in one way and the stars in a slightly different way. By running these simulations, it becomes possible to figure out where did those stars get left behind as the gas and dust continued to funnel and form and collide and eventually make a much bigger galaxy. Following these models through, scientists are now looking to try and find what they refer to as pristine stars. These are the population 3 stars that we were discussing yesterday that are being sought by scientists like Dr. Tim Beers up at Notre Dame University. These pristine stars are formed out of, that first massive generation of stars that died while the small stars were still starting to form. These smaller stars made from a single generation of supernova events have signatures of exactly what was formed in those first supernova. And by understanding what was formed in those first supernova, we can start to get a handle on, what happened with those supernova. We can start to model the nuclear reactions, the nucleosynthesis that took place in these early massive stars. We can then trace out where these pristine stars are located to understand how galaxies formed. It turns out if you want to understand the universe, you have to understand the individual stars first. Now, continuing to talk about stars, but this time, looking at something a little bit more straightforward. Computer simulations that have taken place, and here I have to look at the name of the institution, and I apologize for how I'm going to mispronounce this. Computer simulations done at Witwatersrand University in South Africa have shown that it's actually entirely possible to get stable planets orbiting triple star systems. Now, getting a stable triple star system itself is actually a bit of a challenge. What you need, which is what is shown in this picture, is two stars that are orbiting very close together, and a third star that is orbiting at a greater distance, such that gravitationally this system can be modeled as, well, a binary system that's treated as one star and another star treated as one star. But then we can also model what's happening in that other star as, well, two binaries, or rather one binary. So the way to view it is one big star, two little stars that gravitationally are acting like one star. So it's not really a three-body interaction. It just happens to be three bodies acting like two. Well, in studying a variety of different configurations of these stable three-body systems, what they're finding is it's possible to also have stable planets in three-body systems. So the number of places we need to go looking for planets has increased once again. It seems to be that there is absolutely no limit in where our universe sticks planets, as long as those places have enough metals to have planets. Globular clusters still seem to be a giant nope when it comes to creating worlds we can study. Now, continuing to, talk about worlds, let's jump back to the planet Mars. Trying to understand the mineralogy of Mars is one of those things that we need to really do before we can fully understand what will we be capable of building, of finding, what resources are available to future colonists and future robots who build other robots that may be venturing off to this red world. Right now, we have Curiosity in its little oven traveling across the surface, scooping up samples. This is just the latest in a series of robots that have had a mission to figure out the composition of the red planet. Starting with the Viking probes, we have been digging into the Martian surface, scooping up dust and sand, and sticking it into, a variety of different devices that tell us exactly what is in the soil. We've found all sorts of different things, including, unfortunately, perchlorates that were discovered by the Phoenix lander, which landed in the polar regions, and that particular mineral tends to be kind of deadly to life. Now, beyond looking at individual missions, a team of scientists working at Carnegie, so there is Carnegie University and there are the Carnegie Science Centers. This is a Carnegie researcher that has gone through and data mined all there is to be learned from a variety of the different missions, and has put particular focus into going through all of the data coming from the Mars Curiosity rover's chemistry and mineral instrument. This is CHIMIN. By going through and data mining, they have found a new, more vivid picture of all of the minerals that are present. Now, one of the reasons that it's kind of difficult to get at the minerals is the way that the ChemMin works is it bakes all of its samples, separates out the different parts, and then we look to see what are the parts, and we use the parts to get a better idea of the whole. Now, one of the things that they've been trying to figure out is, for instance, what are the kinds of feldspar? It's a kind of rock. What are the kinds of feldspar that exist on Mars? And any one particular individual sample doesn't have the calibration necessary to say this is this particular type of feldspar or it is this other kind of feldspar. By looking at the data set as a whole, this team has been able to tease out these kinds of data. So as he puts it, I scoured the literature, gathering and analyzing thousands of measurements of both mineral compositions and unit cell dimensions. He's measuring how big are the crystals that are part of that feldspar, and determined a mathematical connection between them. Once this relationship was established, it could be used to glean a much more detailed picture of the minerals in Martian samples. So now he's able to determine the specific compositions of different feldspars that have been sampled in different locations on Mars, allowing us to get a better understanding of how, well, different minerals formed in different places, which also helps us to understand what is the difference in the atoms available and what was the difference in the water available when these minerals formed. Overall, this is the kind of research that is remarkably tedious to do. Doesn't sound entirely exciting as I explain it. It's basically baking rocks, measuring what's in them, and then running it through a computer model. But it's the necessary research that will allow us to know if we land here, this is the kind of minerals that will be available as building materials and available for processing to help us, well, build more robots of armies to go out, more robot armies to go out and further explore the surface of Mars. Now, in one final planetary tale, we turn to a new institution and a new study of exoplanets. This news comes to us from the University of Virginia, where graduate student Jake Turner is trying to figure out how do we better figure out what worlds orbiting other stars are capable of supporting life. We know that life itself requires three things. It requires some sort of a solvent to allow the various molecular processes necessary for life to take place. In human beings, that's water. In other life forms, it could be something like methane. So life requires a solvent, basically to eat. It requires some sort of a thermal gradient to cause chemical processes to take place. So here on Earth, we have sunlight at the surface. We have deep ocean volcanic activity to drive thermal gradients beneath the seas. Life also requires nutrients of some kind. This can either be various minerals or it can be, let's face it, some of us like to eat plants. So whatever your combination, you need a solvent, you need a thermal gradient, and you need nutrients to be those building blocks of life. But in order for those building blocks of life to have a chance to, well, keep doing their biological thing, you also need a world where you're probably not getting radiated to death. Here on the surface of the Earth, we're able to have life because the Earth has a fairly significant magnetic field that protects us from cosmic rays. It protects us from a lot of solar radiation. And we can see this protection happening when we see the aurora borealis in the north and the aurora australis in the south. Now, other worlds such as Mars don't have these strong magnetic fields, and as a result, the solar wind is able to blow away its atmosphere, and its surface suffers a much higher dose of radiation than is sustainable for life over the long run. Now, if we want to imagine life existing on a surface, this tells us what we need in order for life to survive is a magnetic field. What Jake Turner has been working on doing out at the University of Virginia is figuring out how can we detect these kinds of magnetic fields. And what he's doing is looking around our solar system at what are the observable signals of, well, magnetic fields in our own solar system's planets. What he's finding is these magnetic fields produce radio waves. This is why you can use your AM/FM radio to detect Jupiter. This is also why, in fact, we can detect all the worlds with increasingly sensitive radio detectors. Now, if we can detect our own world's magnetic fields using radio detectors, we should be able to use the exact same kind of technique, but on much more sensitive systems to detect if there are magnetic fields around extrasolar planets, these planets that orbit other stars than our sun. So this graduate student, Jake Turner, and I just love that this is a student's work, is currently in the process of working to develop the kinds of sensors and techniques that are necessary to make these kinds of discoveries. As we get tests turning on in the near future, this is a new exoplanet searching telescope that is on its way to a final orbit around the Earth-Mars system, Earth-Moon system, rather. As it starts searching the nearest stars for planets, these will be the kinds of targets that this kind of detector is able to follow up on and say, here is a planet, thank you, Tess, for that information. And now, let me add, here is a magnetic field. So here's to hoping that in the not too distant future, we are able to combine these techniques and find nearby worlds that just might be capable of supporting life. Now, I have one final story, and I'm finding I don't have a picture for that final story. So that is confusing. Looking to see if I can pull up a picture. Yes, I can. So let me open a picture real fast, and I can go into one final story of the day. This one involving Alpha Centauri. Now, Alpha Centauri is the nearest star system to our own planet Earth. This is a 3-star system, such as we talked about earlier today, and this 3-star system appears to be hiding planets. Now, one of the other things necessary for us to safely go explore these worlds is knowing if there are X-ray emissions from these 3 stars that just might zot any spacecraft we send in that direction. For the past decade, the Chandra X-ray Observatory has been systematically studying this system and has found and is finally able to announce that there aren't the kinds of X-ray emissions that we need to worry about coming from this particular system. So it seems that one particular kind of hazard isn't something that we need to worry about. Now, what they've been looking at is the 2 brightest stars in this system. This is Alpha Centauri A and B. Proxima currently holds the title as the nearest star, but it's not quite as big and interesting a system as these 2 giant stars might be. So that kind of rounds out today's set of stories, and I'm now going to pull up the chat and ask, do you have any questions? I'm going to take questions for about the next 30 minutes, and then we're going to flip on over to a NASA press conference on new results coming to us from the Mars Curiosity rover. So if you can go ahead and at me with your questions, it will make it a whole lot easier for me to find them. So thanks a lot. This has once again been the Daily Space for June 7th, 2018. I am your host, Dr. Pamela Gay, and this is a production of CosmoQuest. If you would like to help us do science over at CosmoQuest.org, we currently have a need for volunteers who could be you to help us map out Mars and Mercury. These 2 little worlds are covered in craters, and we're trying to understand what those craters tell us. A few minutes a day could mean a lot to our team scientists. Now, CosmoQuest is a collaboration of many different institutions, and our lead institution is the Astronomical Society of the Pacific, a 501c3 nonprofit dedicated to putting science in your brain. Our partners include the Planetary Science Institute, McCrell International, Youngstown State University, and many others. So if you would like to see all the different content we produce, please give this channel a follow. If you want to help sustain our efforts, every subscription and every bit helps. So now I am trying to find where in all my windows I have hidden your questions. And I'd like to say thank you for the 1 bit. Oh man, my audio is low and I missed it. I'm so sorry, everyone. I'm now going to fix it belatedly. Testing. I'm so sorry that I had low audio the entire time. I am sad. I have now fixed my cable. So sorry. I need to replace my audio cable. Yeah, I do. Sorry about that. I do need to put an audio cable on the wish list. Okay, please give me questions, and I'm actually going to add an audio cable to the wish list while you get your questions in. So what you're hearing is my air conditioning unit. I'm sorry, but I can suffer for a few minutes. Our house doesn't have central air. So Hanny asked, thank you, Keeper, for bringing that forward. Could there be stars that are still alive from the very early era? Yes. So we had a first generation of massive stars that lived and died before the first regular stars had a chance to form. The first regular stars that formed, the smaller ones of these are very much still alive. These are the population 3 stars that we're constantly looking for. What was the first bit of news? CosmoQuest. Think most of us were fiddling with our audio. Oh, I'm so sorry. So the first story was about the Juno mission has been granted a extra 41 months of funding. This new funding is to support the spacecraft as it moves into what will be a less stressful set of orbits. Currently, the Juno mission is orbiting Jupiter about every 14 days. They're going to move into a larger 51-day orbit, and this will put less stress on the spacecraft's engines. But in order for the spacecraft to complete all of the science it wanted to do, it needs a longer duration to complete all the orbits. The science that it's completing is related to the number of orbits, not to the number of days. I'm now trying to figure out what type of USB cable I have. It's not micro, mini, it's mini. I tried macro, and macro was not the right word. So hang on a moment while I work on adding a new cable to my wish list. And I'm going to add a higher quality one. This particular cable goes through a bit of a hard life because it gets plugged and unplugged at the beginning and end of every time I record. Let's try this one. This is just $5. It will be faster if I just order the dang thing. Let me make sure it's the right kind of cable. Show me the end. You aren't showing me the end. You are a micro cable. Okay, let me continue my search for a mini cable that is braided instead of There we go. 6-foot mini. You say power. Aha, you are a data cable. I don't know if you're high speed though, because you were designed. Sorry, you are now all watching me hunt for a cable. So what I would rather is, instead of you spending $7, can you please, please, please find me a high quality 6-foot long mini cable, not micro, mini USB cable. Because honestly, identifying a high quality cable that is 6 foot long has been why this cable purchase has been delayed. So information is needed, dear stream. And then I shall transition. Yes, it's USB 2. I have an older system. I need a high quality USB 2 cable that is a mini. So Guido is asking, what do I think the presser is going to be about? I have no idea. 99% of the time, it seems like a press conference related to Mars is just going to be, we've discovered water-related things. So, for all I know, it's going to be yet again a water-related thing, but I don't know for certain. So I keep hoping. That you will be able to find, they will be able to find symptoms of life. Symptoms, I use that word because it won't be direct evidence. Whatever we find is going to be fossilized or desiccated. And I don't think we have sensitive enough instruments on Curiosity to be able to say, aha, this has DNA. What I'm hoping is, there had been some interesting discussion a few months ago of some rocks that looked kind of like mats that you get of fossilized algae. I'm kind of hoping, but this is a personal hope based on zero information and 100% pure wish and conjecture. Pure wish. There is no conjecture involved. 100% pure wish. What I'm wishing the presser will be about is new minerals that appear to be similar to things. I think, yes, stromatolites. I think that's the correct term, keeper of maps. I'm hoping that they're going to talk about minerals that appear to be consistent with the kinds of minerals that we find on seashores here on Earth, or former things. So we see lots of stuff that pareidolia, our desire to find shapes in things where those shapes don't exist. People have found everything from Bigfoot in the shape of rocks to things that look like fossils. The thing that was in the, I think it was the Guardian, yes, not the Guardian, it was in the Daily News in London yesterday. That was just a rock. We have in the past seen different layers in the strata that Curiosity was driving past that appeared tantalizingly like algae mats that were fossilized. But that's not to say that's what they were. That's just to say that's what several of us looking at the images imagined we could see, and we're all now desperately waiting for more data, closer up views, all those sorts of things. Because pareidolia is real, we do see patterns where they don't actually exist. Yeah, I do backflips for stromolites. Yeah. Stromatter. I'm determined to leave out the middle syllable on that. So there's lots of tantalizing stuff out there. Do we have any other questions out there? That sentence had terrible structure. Sorry about that. And once again, if you like what you see, give us a follow. So I'm going to go ahead and tweet about the upcoming, words, they're hard, the upcoming press conference. Sorry, I have too many messages across the screen and my brain had to do a hard reset. I can't find my window. Man, tweeting is hard. We are about 15 men away from NASA's press conf about new Mars Curiosity results. I'll be on Twitch covering it all, and covering it all, period. Come join the chat as we learn together what is new and exciting on the red planet. Okay, so it has been tweeted. So Hanny is saying, if you did not answer before, does Earth have many more minerals than Mars? If so, could that be attributed to life or size? So Mars and Earth have the same chemical composition, but the chemicals are in different ratios. So there's that factor. And we have a whole lot more water actively on our surface. This means that short-lived minerals that get torn apart by ultraviolet light or changed into something different by ultraviolet light have the ability to exist on our planet. The processes of water flowing through our world has done interesting things. Of course, dead animals create oils and things that you don't otherwise get. So I'm betting we're not going to find coal, which I guess counts as a mineral, on Mars. So there will be differences. In general, it's my understanding that any mineral that exists on Mars also exists on Earth. I don't know if the reverse is true. One of my most strongly remembered moments attending my very first planetary science meeting was everyone was talking about a mineral called olivine, and I couldn't figure out why everyone was excited about olivine. It's something you can buy in jewelry. It's pretty. It's a rock. And it turned out that, thank you for the host, Dr. WD40. So it turns out that one of the things that is most exciting about olivine is it forms in water. So the fact that we've discovered olivine on Mars indicates that there had to be water on Mars to form the olivine. Okay, I saw there's another question. This one's from Fenrig. Fraser, and there's no I in his name. Fraser Kane posted a link on Twitter the other day to a paper that claims icy worlds like Europa might lack the basic ingredients for life, like phosphorus. Any truth to that? We don't know. this is one of the sad realities is theory papers like this could be true, but the universe keeps surprising us with what it does. So yeah, it's possible, but I don't think it necessarily has to be true. We just don't know enough yet. One of the questions that I want to know, thank you so much, Stonesirs, for the subscription. One of the things I really want to know is what is the inside of these icy bodies like? So I keep wondering, if you melt down an icy object, do you basically find an asteroid trapped inside? Part of me suspects that just might be the case, that on the inside, these objects are essentially just, thank you, Samantaj, for the cheer. Part of me suspects that if you, and I'm going to switch views here, if you melt down a Kuiper belt object, what you're going to find on the inside is essentially the same kind of stuff that we have forming asteroids. It's just because the comets, the Kuiper belt objects, they all formed in the outer solar system. They weren't getting blasted with the massive flares of heat that dried out the inner solar system. Hanny, it wasn't very recently, but I'm not... well, I appreciate Salmon or Saman when people pass by and leave bits. Thank you. So, Hanny, I don't think we know exactly when Venus became such a hellspawn of a planet. And since I don't really know that, I can't really answer. So I see that Bajeffis is asking, what is the latest news around surviving the radiation levels on Mars? You have to go underground. It's just that simple as far as we know. There have been recent studies coming from the various Mars robots on the surface that boiled down to it's not as bad as we thought. But there's a difference between not as bad as we thought and is going to give you cancer anyways. So in order to decrease the risk to, human beings who like to live, we do need to worry about just how much radiation there is. Now I'm going to continue answering your questions. And while I do it, I'm also going to be working on getting NASA TV all set up and the audio correctly feeding in. But first, I'm going to see what Dr. WD-40 did. So that is one way to threaten your students. I appreciate that. There's so much memorization in what you do. The other day I was watching your stream and you're like, muscles aren't that hard because their names are connected to the bones. And I'm thinking, that requires you to know all of the names of the bones. So it's basically turtles all the way down. Yeah. Okay, so I am working to set up my system to allow both of us to hopefully hear what's going to be coming from NASA TV. This is going to take me just a minute. You shouldn't lose my audio in the process. I just need to make sure that everything is going right. So I want to be listening to headphones, and I'm going to switch over which screen I'm using. And apparently you're going to get to see my audio preferences. Let me move NASA. Okay, so I don't quite have my audio capture working. So currently it's just an advertisement. NASA has advertisements for some of its challenge projects. Okay, I need my MIDI software. Sorry for all of the issues. So that's set to an aggregate device. Still working on the audio. We don't know, Hanny. My wishful thinking, and I fully admit this is wishful thinking. My wishful thinking is that what we're going to get to hear, see, whatever, is that this is all about rocks that are cool and have different things going on. So my aggregate device doesn't want to work. Built-in output. Why don't you want to work? So it turns out audio settings are always black magic. I have everything set up the way I always have it set up, and it's like, no, you aren't allowed to hear anything. I have it successfully going into my ears. I just need to get it going into yours. So let's try that. Okay, so now you have it. I have it. We all have it. We all have audio. Okay. Okay, so while we wait, let me see if I can line this up a little bit better for you. There we go. Okay. So it wasn't where that slider was. It's apparently sometimes the exact, just a snort to the left. Okay, so you're telling me it's just a snort too loud. Okay, I can make it a snort softer. There we go. Oh, let's all do the time warp again. I agree, Paranor. Let's all do the time warp again. Oh, you want the video a snort to the left. What? Trying. Oh, I have to shrink it to go a snort to the left. Okay. It's... So there's that side lined up. There is... I'm invoking incantations here as I do this. I think this is about as perfectly lined up as I can get it. I hate when it moves when I pick my finger up off the trackpad. So yeah, I am just as... What do you mean Hermione is on the other channel as well? Paranor, I don't understand. No more touching. You're referring to which things are where. Okay, so we are now here for the time We are waiting for it to start. I'm sure there's mad scrambling going on in the studio that they're using. We are here. Yes, I'm a squirrel. You knew this. Okay, I can fix the tiny amounts of black. Let me make my OBS screen bigger. If I click on links in Slack, I don't know where they're going to appear, Keeper of Maps. Dr. WD40, since it's now 101, I suspect there's some amount of franticism going on. That would be 2:02 Eastern or 2:01 Eastern. There we go. Or at least the music changed. Did they run out of music? The time went away. Oh dear. That's disturbing. Here we go.
Welcome. We are live at NASA today from 2 locations. We're here at the Goddard Space Flight Center, and with me I have Dr. Paul Mahaffey, who is actually our director of the Solar System Exploration Division, and he's also the principal investigator for the SAM instrument, which we're going to be talking about.
This is Michelle Fowler speaking.
Who has one of the coolest titles I know of at NASA, which is actually an astrobiologist. And we're also here at another location today as well, NASA's Jet Propulsion Laboratory in California. And here we have Dr. Chris Webster, who is a senior research scientist at JPL. And we also have Ashwin Basavada, who is the project scientist for the Mars Science Laboratory. My name is Michelle Fowler. I'm an astronomer here at NASA. And one of the things I'm going to say right off the bat today is that none of us live in a vacuum. We all have our own social media accounts, and we're sort of aware of the interest that this has generated. So I'm going to tell you right now, what we're not announcing today is the detection of life. We're not going to be talking about that. What we are talking about are some really exciting new results that have to do with organic molecules. Now, organic molecules are what we understand of as the building blocks of life. And even if we're not announcing the detection of life today, I think that the discoveries we're going to be talking about are a really important next step into finding out whether Mars was once habitable or might even still be habitable. So what I'm going to do now is actually lead it off with Paul Mahaffey, who's going to talk to us a bit about what we know and what we don't know about Mars. So Paul, straight up, what have we found?
Really exciting times. I'll reinforce what you said. I mean, organic compounds on Earth just so much bear the imprint of life that it's very natural for us to equate finding organics on Mars with finding life. But that's not the bottom line of what we're trying to get out here.
Thank you for the raid.
Is that we've greatly expanded our search for organic compounds, which ultimately are fundamental to our search for life. And it's really interesting, kind of 2 complementary results. One result is organics from billion-year-old rocks that got trapped in the rocks in an ancient lake billions of years ago. And the second really is the simplest organic, methane in the atmosphere. And those 2 results, Jen Eichenbrod and Chris Webster, the lead author on these papers, are going to talk about. But let me just set a little bit of the context. It was kind of August 2012, more than 5 years ago. We came barreling into Mars, and there was that exciting 7 minutes of terror. And we landed safely on the surface thanks to the great engineering team at JPL that got us there. But the objective of the mission really was to explore a habitable environment on Mars. And right off the bat, we just found incredible things. We found clays that were formed by water. The rover Curiosity is just extremely capable. It takes stereo pictures. It measures the elemental composition of the rocks. It does some mineralogy. And what we've always done, even though we found many things with the experiment we're going to talk about today, which is SAM, the Sample Analysis of Mars experiment, we essentially found out very early that this was a habitable environment. Water had been there for a very, very long time. With our SAM experiment, we found some interesting things. For example, how old the rocks were, how long they had been exposed to cosmic radiation. Measurements of light versus heavy elements told us about how the atmosphere had escaped over billions of years. But we've kept going on this search for organics, and we had found some methane before. We had found some simple organic molecules before, but we greatly expanded the search with the results we're going to talk about today. So it's really exciting.
So Paul's just mentioned some of the results we're talking about today, and one of the things that's really important is you can be involved in our discussion. So throughout the broadcast today, you'll see me looking down at my iPad. We're taking live questions. So if you're on social media, you can use hashtag #AskNASA. Or if you're joining us on Facebook, just put your questions in the Facebook comments and we'll get to as many of them as we possibly can. And we're also going to be taking questions live from the media a little bit later in the show. So I'll actually be here live looking at your questions, and I can give them to whatever scientist is probably the most appropriate. So now we're going to go to Jen. So Jennifer, tell us a bit about, why is it significant that we found organics on Mars?
We found organic molecules in rocks from an ancient lake bed. Those organic molecules could have come from life. We don't know that there was ever life on Mars. The organic molecules that we found are not specifically evidence of life, because there are other sources of making those molecules, including things that are non-biological in nature, things like meteorites, or even rock processes. We can attribute geology all by itself without life to making organic molecules. And the information that we have doesn't tell us which source is responsible for what we have.
Well, thank you. So another one of the major detections and discoveries we're talking about today involves methane on Mars. And methane is something that we think of as natural gas. It's a simple organic molecule. And I'm going to talk to Chris Webster at JPL right now.
Methane is seasonal on Mars.
Discovery before of methane spikes. The level of methane went up very dramatically on Mars. So Chris, you've reported before on these methane spikes. Can you tell us a bit about what today is different and noteworthy about methane on Mars?
Well, Michelle, as you know, every chapter in the story of methane on Mars has been a surprise. From some time ago, there were reports of plumes in the atmosphere of methane. There were reports of patches when orbiters looked at it, and spikes that we reported, as you just mentioned. Every one of them a surprise, but problematic in the sense, frustrating, because none of them were repeatable in time and space. They seem to show that methane was misbehaving. It was sporadic or almost random pulses and patches were showing up. So today we're announcing a discovery of a repeatable, identifiable seasonal pattern in the methane measurements. And we can look here at the graphic and we can see that. It's in the lower background level, because most of the time we're not looking at spikes, and we see this low background level. You can see from the winter to the summer this growth. And the big surprise, too, is not only have we got this wonderful repeatability, but the seasonal cycle changes by a factor of 3. That's a huge change, completely unexpected. And what it does, it gives us a key to unlocking.
Seasonal means not volcanic.
We have something to test our models and our understanding against. And we'll hear a little more about that later.
So one of the things you're hearing a lot about today is the term organic, and this is something that a lot of people are familiar with in many different ways. So I'm going to talk to Jennifer Eigenbrode. So Jennifer, tell us a bit about what do we mean by organic, and tell us about what is so significant about finding organics on Mars.
Right, so organic molecules to a chemist are simply molecules formed of carbon and hydrogen. Sometimes there's other things that go in that, such as sulfur, nitrogen, oxygen, phosphorus. However, to a chemist, it's just that type of a structure. What we're not talking about is molecules that specifically come from life, and we're really not referring to the organic stuff that you find at the grocery store, which is that pesticide-free produce that we get. They're very different things.
So it seems to be kind of amazing. I mean, this is one of the engineering feats of the Mars Curiosity rover, is that we're finding molecules. We have a chemical laboratory on another planet. Can you talk to us about how we identify these molecules on another planet all the way on Mars?
Sure. So the Curiosity rover drills into rock layers. And when it does, it produces a rock powder, and that rock powder gets put into the SAM oven and heated. And when it's heated, it produces gases. They get whiffed off into the mass spectrometer. Here you can see the gases coming through some tubes, and they enter into this chamber where electrons ionize that material. As a result, you have molecules that are split into tiny little pieces, and the mass spectrometer can then identify what those different pieces are, and we can put them back together to understand what the original molecule was. Now, there's another feature of SAM. That is, it has a gas chromatograph. And the gas chromatograph looks a little bit like this. It's a really, really long tube, and it has a hole in it that's about the width of a human hair. Now, the column allows molecules to go through it, and they go down this long, long tube.
So what she's explaining is they accelerate things, and the technique they use for acceleration actually splits up different masses end up getting accelerated in different ways. And we measure how fast they come out, what deflection they have when they come out. And this is how we figure out what molecules are involved. Now, everything gets shredded going in. So any life would be shredded.
Talking about drilling into the surface of Mars with the arm of Sam, how far in do we go? How far deep into the surface?
5 centimeters. That's about as far as we can go. Yeah, 5 centimeters.
We'll talk a little bit more, John, about why that's significant. There may be even more interesting things farther down. So the thing that really amazes me, and I remember very well the landing of the Curiosity rover as one of the best nights, early mornings of my life. When you showed me that tiny gas chromatograph coil, you know, that had to actually land on Mars. At one point going through the atmosphere, there was a big snap of G-forces, like up to 10 times the force of gravity. We actually land these incredibly sensitive, sophisticated instruments on Mars. And I want to talk a little bit more about that. So we're going to go to our friend Ashwin at JPL. So tell us where you are and tell us a bit about the Curiosity rover, the larger rover.
So seasonal methane could be related to melting ices.
And what you see behind me is actually the test model of the Curiosity rover. It's a twin, basically, that we use for testing here on Earth. The one on Mars is in a place called Gale Crater. We sent it there. It's about a 100-mile diameter hole in the ground that formed when a giant impact occurred on Mars about 4 billion years ago. But what drew us to this crater is the mountain that you see in the middle of it. This mountain wasn't there when the crater formed. In fact, it formed as sediment was carried in by rivers and streams and then deposited into this giant lake that filled the crater. And as that sediment settled out from the water, it built up the layers that then made up the mountain. Each layer of this mountain is younger than the one below it. So by climbing this mountain with the rover, we can read the ancient history of Mars. And climbing is exactly what we've been doing throughout most of Curiosity's mission. We're now 1,000 feet above the crater floor. That's as high as some of the skyscrapers in downtown Los Angeles. And we get this amazing view. And so the progress has just been to continually drill each layer of this mountain. And the samples that Jen described were taken from the lowest part of the mountain about a few years ago in 2015. And it's taken us a few years to get an understanding of these results so that we can describe them to you today.
So essentially they landed in the bottom of Gale Crater, and now they're climbing up the edge, not the edge, they're just climbing upwards and measuring layers by essentially going, drilling.
With these rocks because of the orbiters that have been at Mars before us. So for example, there's the Mars Reconnaissance Orbiter and there's Mars Express, and both of those instruments both of those orbiters had instruments capable of detecting clay minerals at the site. So we know that some of the layers in the mountain are made of clay minerals, which means that water had interacted with them. We weren't sure though if rivers and lakes actually existed, and Curiosity has now shown that lakes existed for a long time, probably hundreds of thousands, if not millions of years.
So the question was the water transitory? Comet hit, temporarily had a thing of water, and then it went away instantly. They've now determined, no, the water that came from comets stayed.
You know, this is really worth a press conference of its own. You know, it's just sort of coincidence that we have this amazing week to tell you not only about the success of the drill, but about these wonderful results from the last few years of exploration as well. In late 2016, we realized that one of the main motors of the drill was no longer functioning reliably. This basically meant the drill was dead, and a big part of what we could accomplish on Mars, we'd no longer be able to do. It's not just that we fixed something or tweaked something, we had to invent a whole new way of drilling. And that's just a remarkable story that really I have to give all the credit to the engineers at JPL who did that work. So for about a year and a half, they tried to fix the motor, then invent this entire new way of drilling that didn't use that motor any longer. And just this week, we have achieved success. We've now successfully drilled and analyzed samples with our laboratories once again.
So we're talking about drilling down and analyzing these samples. And for those of you that are a fan of organic chemistry, we're actually going to dive into the details just a little bit right now. So Jen, tell me the details about what was detected.
Right, so we detected a variety of molecules, including some that have carbons linked in a ring structure, such as benzene, and others that include carbon chains. And here's an example, propane. Now, these are just representative of molecules small little bits and pieces of molecules, but because we see these coming off of the sample at high temperatures, what they're really telling us is that they're part of something larger, a macromolecule. And this is just an example of something we find on Earth. We call it kerogen. Now we find examples of kerogen on Earth in things like coal and black shale, these two things, right? And we also find them in meteorites, so they're common. This tells us that there is organic material in the rock in a different form than what Sam detected. And what it means is that it was in a robust form. This form of organic matter resistant to changes. Now, the other thing that we found was thiophene. And this is an example of some of the data we'd get from Sam. We can actually tell after the molecules go through the GC column the actual structure. We use this information to figure out this type of structure. So here we have 4 carbons and a sulfur. Now sulfur looks like this when it's in rock form. But in the sample, the sulfur is probably in the organic molecules themselves. And that's important because sulfur actually is the material that can help bind all these small pieces of organic molecules together into something really big, like that large molecule I showed you. And sulfur helps to resist oxidation. That's really important for our discovery because we are looking at ancient rocks that are 3.5 billion years old, and we found organic materials inside them. However,
so 3.5 billion years ago is about when the moon was formed.
The surface is exposed to a lot of ionizing radiation.
Sorry, wrong date. Is about when the heavy bombardment was.
And all of those can degrade organic materials. And so that rock has been sitting at the surface for an extended period of time. We're talking tens of thousands to hundreds of thousands of years. And that's a long time for all these changes to happen. There were a lot of people who thought we weren't going to find all the organic molecules that we did. For instance, Viking started this quest back in 1976, looking for organic molecules. Curiosity has continued that quest. And now we have a diverse set of molecules that we can now start to understand a little bit more about how this material is preserved and where else we might look to get more.
This is a pretty amazing thing. I mean, you know, working on Mars is very hard. I mean, a lot of people know that Mars has almost no atmosphere compared to the Earth, about 1% the atmospheric pressure of the Earth. It has very high radiation levels because Mars isn't protected the way the Earth is by an active magnetic field as well as a thick atmosphere.
That's right.
So we have this laboratory working on Mars. And so the radiation from the sun gets about how far down into the soil?
It's coming from the sun, but it's also coming from the galaxy.
Right.
And it can extend about 1.5 meters down, maybe even a little bit more, it depends on what model you use. But there are places that you can go deeper down that we might be able to tap into molecules that aren't disrupted by the radiation itself. And the ExoMars rover is a perfect example. It's going to drill 2 meters deep. This is the European Space Agency's ExoMars rover. And it's going to drill 2 meters deep, and it will have the opportunity to examine materials at the surface and on the way down to see if there's comparisons. We'll learn how important it is to where we have to refine our analyses, where we'll understand the preservation issue and how it affects things at the surface as compared to things further down. But most importantly, if there are biosignatures inside that organic material or associated with it, we're going to have a better chance of understanding that if we get to materials that are not exposed to all this radiation.
That's one of the things today. We're finding some very interesting chemistry right up on the surface of Mars, and it's a promise of even more interesting chemistry to come if we can get a little bit deeper down underneath that. So, you know, we're looking at Gale Crater, and you know, so how did these organics get here? I mean, we're finding these organic molecules now.
So to put this in layman's terms, they've been going along, picking up rocks, and then doing mass spectrometry, which is the exact same thing that criminal investigators do to figure out what is the composition of that ash that you find, what is the composition of that blood you find. This mass spectrometry turned up the kinds of molecules that are present in life. Now, because everything got ground up, because everything got baked in the oven to allow the mass spectrometer to work, they can't say, this came from this complex molecule, this came from this complex molecule. What they can say, it is consistent with these molecules. And these molecules would only exist if the water had been on Mars for thousands of years instead of for just a small amount of time. So this is telling us Mars was definitely wet for a prolonged period of time because it allowed cool water-requiring minerals to form that are now getting drilled up and sampled.
If you take the organic detection in the ancient rocks and you just generalize it, we have found organic material in the subsurface. And that might be representative of organic material throughout a grander area. And that is carbon that could go through various processes and make its way to the surface and turn into things like methane and then seep into the atmosphere. Now, the detection that Chris is going to talk about is about modern day methane, as opposed to ancient signals, what I discovered in the rocks.
All right, so with that, we're going to go over to Chris Webster back at JPL. And so Chris, tell me a bit about the seasonality of methane. Give us some detail about this new discovery.
Well, I thought I'd tell you right away that we've seen the seasonal variation, and we've tried to look at the data and come up with some explanations. And we've been able to rule out some of the sources. We don't actually think the meteoritic or delivery of interplanetary dust that can produce methane in the atmosphere, as Jen said, we don't think that's so important because we wouldn't expect to see a large seasonal variation. We might see 20%. Instead, we're seeing this massive change in the methane signal. And so what we consider, we look at the data, and the idea that best fits our data is the idea of subsurface storage. So way under the ground, under Mars, there's methane that's trapped. It may be trapped as clathrates or other materials. We don't know if that methane is ancient. We don't know if it's modern. It could be either. And we also don't know if that methane was created from water rock chemistry like serpentinization, or it was created by methanogen microbes. We cannot distinguish that. But the methane leaks or seeps up to the surface, we believe, and finds its way through cracks and fissures. And eventually, when it gets to the surface, we're then in a situation where the surface temperature can modulate or especially amplify the release of methane. So this is an exciting time because we have this seasonal cycle to constrain some of the theories and of the sources and sinks of this important gas.
Now, Chris, I want to talk to you a bit more about.
So what this means is as the temperatures warm, something happens that allow methane created down deep to escape through the now thawed surface.
Well, it's we're ingesting from the air, and if you look at Curiosity, around about waist height, there are two inlets, two little valves, and these valves allow the Martian atmosphere into our sample cell. Once it gets into SAM and into the tunable laser spectrometer in particular, we have tiny little infrared laser beam that multi-passes. It bounces 81 times between these mirrors, and that amplifies its sensitivity. So when you look at the laser light on a detector, you can scan the laser and look for the spectrum of methane. And the resolution, the spectral resolution is so high that we see individual methane lines, and in particular, we see a fingerprint of 3 lines together that can only be from methane. So our measurement is unambiguous. The signals we see, they come from methane and nothing else. And secondly, we measure them with high precision.
So let's go to the two different scenarios as to what would be causing the methane. I guess one is that we have a seasonal cycle because bacteria under the surface of Mars would be more active in the summer. Is that the idea?
That's a possible idea, but again, we cannot distinguish that from serpentinization.
Translation: don't force me to say something like that. I don't want the hate mail.
Once you get the hydrogen released in both in that reaction, it can be catalyzed either through metal catalyzed methane, that's the abiological route, or it can be catalyzed through enzymes in the microbes in the cell potential.
So just sort of putting that into slightly simpler terms, if you have water that's interacting with volcanic minerals like olivine, you can also get similar methane that's trapped in the soil and preferentially comes up in the summer?
Yes, that's exactly right.
Right.
But we're hoping that we'll see more we'll get more results in the future on this, especially from other missions. And as far as testing for the biological source or not, there are several more steps that can be made. We can look at the carbon-13 isotope ratio, for example, that could be suggestive of biological activity. And we can look at the accompaniment of other gases. So we have, and we can sit on the surface in Curiosity, and maybe one day we'll see a plume that's large enough where we can measure that carbon-13 ratio ourselves. So there's lots of exciting ways forward, but at this moment, again, the biological option is being held. It hasn't been ruled out.
So really exciting results about the methane and the seasonal variation of it on Mars. I want to take a moment just to say, for anybody who's been joining us, we're live at NASA. We're at the Goddard Space Flight Center, and we're also at NASA's Jet Propulsion Laboratory. And we'll be taking your questions soon live.
So basically what this all sums up to is there are complex molecules consistent with what we see, where we see prolonged water on the surface, and there is methane that is seasonal at the surface. Now, we don't have the data to say if the surface methane only occurs in certain places. We just know it occurs where Curiosity is. So this is all saying this is consistent with life, and we need to stay tuned. Now, what Michelle's talking about right now is what InSight is going to do. So I'm not actually cutting in. So let's see what else we have coming up next.
Underneath the surface of Mars. Okay, well, before we go on, I do want to make one more trip back to the Mars Curiosity rover and to Ashwin. So, Ashwin, the amazing thing about this seasonal variation of methane that we were just talking about is you need to be there for many seasons. So tell us about the lifetime of the Curiosity rover, and you just give us a sense of what an amazing accomplishment it's been.
Sure. Yeah, this is really wonderful to have this discovery that took so many years to not only take the measurements, but then to analyze as well. The measurements that Chris described come from an instrument called the Tunable Laser Spectrometer within the SAM instrument suite on Mars. And we've taken about 30 measurements with this instrument over the course of the mission. In fact, we're planning one on Mars today. So without having the rover survive for 6 Earth years, 3 Mars years, which is 3 times longer than its original mission, we would have never been able to discover these amazing seasonal patterns that are the heart of what Chris described. And finally, I just wanted to add a few more words to Jen's discoveries. One of the things that makes that so special is the role, how it fulfills the role that Curiosity has played within the Mars exploration program. NASA charged this mission with detecting organics on Mars, and we've certainly done that and expanded the range of organics that we know of today. But it was more than that too. We also wanted to understand how organic molecules, organic matter on Mars that was incorporated in rocks 3 billion years ago would be there for us to survive, would be there for us to discover all those years later. What are the processes and environments that allowed it to resist that degradation? And that really is remarkable from Jen's results, that she's been able to determine what types of molecules and what types of environments allowed those molecules to persist to today. And this is not only important for Curiosity as fulfilling one of our main mission objectives, but it's also important for future Mars missions who will seek direct signs of life. Missions like ExoMars and Mars 2020. And what this does is gives us confidence that when those missions get to Mars, there still can be something for them to discover.
So Ashwin, you were just mentioning that the Martian year is a bit longer than the Earth year, and another thing is that the Martian day, tell us about how similar the Martian day is to an Earth day and how different it is. And I think you actually have some personal stories relating to this.
Well, yeah, there's an enormous number of similarities between Mars and Earth. They're very similar planets in some ways that are purely coincidental. Mars has a 24.5-hour day. And it has a tilt on its axis about 25 degrees, similar to Earth's tilt of 23 degrees, which makes the days and the seasons remarkably Earth-like. It also makes it incredibly interesting to operate a rover in the most efficient way on Mars, because the best way of doing that actually live on a 24 and 37-minute day, which all of us on the Mars Science Laboratory did for the first 90 days of the mission before we all started going crazy.
You just come in about 40 minutes later every day. That would disrupt your sleep, I would think. Yeah.
That's right.
Somebody who's just joined us has asked us, where are you? Give us another sense about where you're standing and what sort of room you're in right now.
Sure. Yeah, we're at the Jet Propulsion Lab.
I love the cardboard boxes that are just piled in the corner. Everywhere has cardboard boxes.
Model of Curiosity lives. So behind us, you see the engineering model. Some people call her Maggie. And she's very much like the one that's on Mars, especially in terms of all the software on board and all the electronics. We have some of the instruments here as well. And this model can drive out into the yard, and we've used it for tests, including solving anomalies that occur on the surface of Mars. This is the model that was used to teach the rover on Mars how to drive and how to navigate. We can use it for a lot of things where we don't want to use the precious time and resources of the actual rover on Mars.
Well, but we're going to start by taking some questions now, but before we do that, I actually want to go back to Paul for just one more last thing. So, we've talked about landing this amazing rover on Mars, and then you have this incredible chemical laboratory on Mars. Tell us that story. How did we get this sensitive chemical laboratory on another planet?
Let me get to that question. You're asking an awful lot of questions. Let me have you throw one in my direction first, and
okay.
that nobody will ask. And what did you do this morning, Paul?
What did you do this morning, Paul?
Thanks for asking. I thought you'd never ask. What we did this morning, actually, was look at data that came down from Curiosity that was deposited into SAM, and it's been months and months. So like Ashwin mentioned, we're just in the process of getting the drill back in order. We're just tremendously excited about that. So the search for organics is going to go on. But getting back to your other question, which is what it took to get the SAM instrument is just very complicated. It took a huge team of scientists and engineers and software programmers. It's an international team. We put this instrument together at NASA Goddard, but Chris Webster's team at Jet Propulsion Lab developed the tunable laser spectrometer. Our French colleagues developed the gas chromatograph mass spectrometer. In fact, this morning they were calling in from Toulouse because they were supporting operations of our instrument from Toulouse. So what we did was we spent several years putting this together, assembled it at Goddard, tested it at Goddard. We put it in environmental chambers that exactly match the conditions we would have on the surface of Mars. We tested out the scripts, the software that we're going to run on Mars. And then eventually we brought it to Jet Propulsion Lab. And this image that you see shows SAM, that's that gold-coated box about the size of a microwave oven, being gently lowered into the rover.
So basically, they build everything, test it out in a lab, make sure it works, then clean it completely and install it.
After everything was perfect, then the rover was ready to ship to the Cape, and everything got launched. So you see everybody there in bunny suits. The reason they're in those white suits is we did not want to bring our skin oils and everything else to Mars, because then Jen would have to report that we were finding things that looked like they came from Chris Webster or somebody else in the clean room at JPL. So it took a lot of work and great teamwork and several nations joining us. It's just been tremendously exciting.
Well, actually, what you were just talking about leads into one of the social media questions. So a person named 3D Physics from Twitter asks, how do you verify that the sensitive experiments haven't been compromised, either before reaching on Mars or after landing on Mars?
Yeah, what we do is we bring along standards, for example. We do what any good analytic chemist does in the lab. We run blanks. So for example, if we're looking to make sure that none of the residual organics in the instrument are producing the signals that we see, we go ahead and we run a full sequence of runs, but we don't put sample in the cup, and then we see what we got. So we work very, very hard to make sure that what we're seeing is from Mars, and we're very confident that, that what we're seeing is from Mars.
Put a different way, they take a picture of nothing, figure out what nothing looks like, then take a picture of their sample, and anything that's in the sample that's not in the nothing is real.
Name you all about, can this methane that we're detecting ever be used as a fuel for future missions? Is it something that's useful for a human presence on Mars? Should we go to Chris for that, or do you want to take a stab at that question, Chris?
Well, of course, there isn't, right now we're seeing low background levels. We're not seeing a lot of methane. Of course, methane is always useful as a fuel. but the ability to extract it from the atmosphere would not be efficient. But if there was a way one could access subsurface reservoirs, then it becomes a whole new ballgame. But that's really speculation at this point.
And I guess I'll, seeing as we're at JPL right now, I'll give another one to Ashwin. So we have a question about if you could have added just one more tool to the rover, what would it have been, right? Well, yeah, what was the thing that you really want on the rover that you just don't happen to have?
That's a tough one. There's probably a whole list of things we could add. I'm going to deflect and just say the next thing we want to do on Mars is exactly what we're doing with the Mars 2020 mission. Building on all the results from habitability and organics and the possibility of life that Curiosity has opened up, and looking ahead to having instruments on Mars that are built specifically to look for those signs of life.
So Jen, this seems like a good one for an astrobiologist. I mean, this is a difficult question. I mean, we have organic molecules. How do you know if they're processed by life? You know, what signs would you look for that might hint to you that this is something based on life?
Well, all life that we know of is based on organic molecules, even though we know that that's not the only way you can make them. So if we're going to go look for life, the first thing you'd want to do is look for signatures associated with organic materials. And that was part of the reason why it's so significant that we found organic materials in the first place. It helps us guide where we're going to look for more of these. Now, in those signatures, they might be things about the chemistry of the organic materials, or perhaps there are things about how the organic materials are stuck together in shapes, how they're packaged. Maybe it's going to be about their isotopes. There's a whole suite of chemical and physical things that we can measure that might indicate signatures of life.
Let me jump in there. I mean, Jen herself went up to Svalbard one time to one of the farthest, most northern springs, a hot spring way up in that cold area. And then we put some of this material in the gas chromatograph mass spectrometer, and these patterns showed up that show the length of the carbon chains, and bingo, that was the signature for life. So those are one of the many types of things we'll look for.
That's right, and there happens to be another experiment on SAM that we haven't used yet. It's one of the wet chemistry experiments. And if those types of things are left behind in the organic material that we come across, assuming we will come across more, perhaps, if it's the right sample and the right compounds are there, maybe we'll get some hints.
So I understand we actually have a media question that they're going to try to feed in on audio. So if I could ask for that question, we're going to try to have an audio feed at the moment.
Thank you. Our first question is from Chris Van Cleve from CBS. Your line is open.
Go ahead, ask your question, please.
Thanks for doing the call here. And forgive me if I missed this at the very beginning, but if you could sort of translate this into terms my grandmother would understand, why is methane so exciting, and what is it that you found that is so intriguing about this organic chemical, or compound molecule that's different than what we kind of already knew, that there were already the building blocks of life potentially on Mars?
Okay, should we go to Chris for the methane question? Did you hear that, Chris?
Yes, I would start right away by saying, whenever you have an oxidizing atmosphere and you see reduced compounds like methane or hydrogen sulfide, they're always very exciting. And in particular for the Mars methane, because 95% of the methane on Earth is produced from biology, it's produced from termites or rice paddies or cows or sheep or termites, etc. Because of that, there's always been this interest in Mars methane as its potential.
So, to be fair, at no point did they say methane is formed only from biologicals, minerals that are melting, and volcanics, and that methane gets destroyed by sunlight. So without saying those four things, it's formed in three ways and destroyed, no one really knows why this matters.
Most of the methane in the atmosphere comes from biology, from rice paddies, or from a lot of different processes. But most of the oxygen on Earth also comes from biology. Billions of years ago, the cyanobacteria got serious, and they started cranking away. And so in our atmosphere, we have both a combination of methane and oxygen. And that's what some of the folks who are building these big telescopes, follow-on telescopes to the James Webb, for example, that are going to be out in space looking at exoplanets, they're going to be looking for combinations of oxidizing and reducing things that might be evidence of life.
There are two completely distinct news bits that are being interwoven even though they're not interrelated. Methane is one story, molecules is another story. Nancy Atkinson.
Hi. There was a similar announcement of detection of both methane and organic materials back in 2014, also by the Curiosity rover. How is this announcement different, or how have you built on the findings from 2014 for this detection?
I know we were just talking about that beforehand, as that being a very good question to ask. So I think, Jen, you want to take that?
Sure. In 2014, we reported the discovery of chlorinated molecules. Now, these are carbon structures that have a chlorine attached to them, and there was a few of them. It was a significant discovery. It was the first time we were able to confirm organic molecules on Mars. It was the first time. And we've been looking for this for a very long time, with the hopes that we would find it with the Viking instruments in 1976, and finally with Curiosity in landing on a lake bed, that we could actually discover these. Now, we were left with, what do these mean? The thing about the chlorinated molecules is that it's not what you typically find in natural samples. And so we weren't sure what the significance was at the time. However, it did give us a lot of motivation to keep looking. There have to be other layers in the Gale crater, other layers of the lake sediments, and we wanted to find more organic molecules. And that's exactly what happened. We drove 4 miles away. We started down at the lowest part of the crater. We drove 4 miles away and got to the base of the mountain, and the first layers that we looked at contain all of this organic material that we're reporting today. So we have essentially expanded upon the inventory of the organic molecules, and now we have a better sense of how they were preserved in the rocks in the first place.
So should mention that your report, Jen, showed significantly greater abundance than we had detected before. And one more thing to add is, in almost every experiment we do, as we heat up the sample in this little quartz cup, we see a big oxygen signal, and the oxygen signal comes from a mineral that breaks apart, that contains chlorine and oxygen. But then the hot oxygen can react with some of the organics and produce carbon dioxide. That's called combustion. And what Jen did with part of her analysis was really to look at the high temperature release of organics that might have escaped some of that destruction. But there's still things there that we're not seeing. So I mean, that's really motivating our desire to get back and, with different techniques, really look for a more comprehensive suite of organics, try and figure out where they really came from.
Right. And Chris, would you like to continue your answer as to why what we're announcing today is different from what was detected before, as far as the seasonality of the methane?
Yes, it's very different, because in the past we were seeing spikes that we couldn't understand, and we had ideas about them, but we couldn't constrain them because they only occurred occasionally. So now first of all, we've measured the background level over 2 years, so we know the total amount of methane in the atmosphere is constrained by that. It's a low average value of only 0.4 parts per billion. It changes a lot, but the total amount is low, so that also constrains the magnitude of pulses and spikes elsewhere that would mix into that atmosphere. So this is a very important observation. The fact that it changes so dramatically, this factor of 3, has got to be duplicated by models that explain it. Now, we do think that the spikes and the low background seasonal cycle are related. It's quite conceivable that the same reservoirs that are slowly seeping methane up to the surface are also occasionally causing large pulses of the gas to be released.
Well, thank you. And I understand we have another media question. So we'll go to the audio line now.
Thank you. Our next question from Leo Enright with Irish Television. Your line is open.
Thanks very much. If I could just summarize, as I understand it, the takeaway is confirmation of a seasonal cycle of methane, and also, quite noticeably, a detection of thiophene in the subsoil. So if I could ask, what follow-up investigations, specifically from the Europeans, could support and add to this? Specifically, the trace gas orbiter presumably can do the kind of isotopic analysis that you can't. So can you foresee that being able to contribute? And secondly, still with ExoMars, but in the future, they're talking about drilling to 2 meters. Is the gas chromatograph on ExoMars the same as the one on MSL, and can it do the work that you say needs to be done?
Let me take a first shot at that, and Chris may want to jump in. First of all, let me say, Leo, it's great to hear somebody saying methane instead of methane, like Chris Webster does all the time. But starting with the ExoMars mission, we're actually very proud of the work that our team did here at Goddard to deliver a mass spectrometer to an experiment on the ExoMars rover, which is planned to launch in 2020. That instrument is called MoMA. And we greatly expand the techniques that we use there to look at these samples that come up from 2 meters below the surface. The first thing we do is totally different. It's never been done before on the surface of another planet. We use a laser, basically, to put a pulse of energy into the sample that's in front of the instrument, and then we let some of those ions up into a mass spectrometer. Has a very high mass range. We can do things like find a high mass peak. It's a very soft ionization technique. And we can do what's called tandem mass spectrometry. We can break that molecule apart into its constituents and really try and get at the structure. It's a very powerful technique. We also have a GCMS, a gas chromatograph mass spectrometer, and that also was a contribution from our French colleagues. They're really good at understanding how to do that separation of gases that Jen talked about. And they do the derivatization chemistry, the chemistry that tries to pull out interesting things like amino acids a little bit differently. We kind of have a lot of fluid in a cup. We puncture the cup and put sample in. And they try and control that a little bit better by having basically a little container that'll break apart at exactly the right temperature, put the derivatization in, and then do separation. The technologies have also advanced a bit. For example, one thing we'd be very interested in finding is chirality, the left and right-handedness of an amino acid, if we're lucky enough to find an amino acid. On life, they're not equivalent, but in meteorites, they're largely equivalent. So with MoMA, we're trying to solve that problem as well. So technology advances and our ability to think through what we can put in place on another planet advances. And maybe Chris should talk about what the European Trace Gas Orbiter, which is also looking for methane, what they hope to find. I understand that's just getting going in operation around Mars, and they've not been doing much.
So one of the things that's interesting is they keep highlighting how NASA and ESA are building very similar spacecraft, but they used to work together on everything. So what we're seeing is the fallout from a few political cycles ago. With NASA budget cuts, we had to cut our role in a whole variety of different missions that were being done collaboratively between the US and the EU. And it's hit the point where the EU just can't trust NASA to complete a mission consistently. There's a lot of people doing a lot of hard work to try and mend these relationships. But currently what we see is Mars 2020 and ExoMars being developed separately as 2 different robotic missions to Mars.
Carbon-13 methane than there is regular methane. And if you want to measure that to 1%, you're stuck with this extremely high sensitivity needed. So if the Trace Gas Orbiter sees significant amounts of methane, they will certainly be able to make that measurement. But if they see mainly the low background levels that we are seeing of 0.4 parts per billion, it's going to be a challenge.
So those are, if you don't mind, we have a limited time for questions, and we've had some pretty technical answers. I actually want to go to some of the middle school students that are actually live tweeting us right now. So apparently I need to call out Mr. Soldy's aerospace class. So you guys are sending us lots of questions. So they're asking us about the implications. Does this discovery have any implications for the future colonization of Mars or human presence on Mars?
Sure, it could. When we have
Henny, they are trying to work together in a complementary manner, but there's also a lot of redundancy.
We don't know what that would be exactly. Perhaps there are organisms there that we don't know about yet. They might be helpful for farming. There might be organic materials that could be used as fuel for both farming organisms, including plants, need carbon in order to turn it into their own biomass. And perhaps there's other ways of using it to generate fuels that people there would actually use. Those have not been fully investigated yet, but I know it's an open book on what technologies we might use in the future on Mars.
And actually, there's sort of a follow-on question to this. So there's Mac from Pier Middle School who asked, would it be possible to bring samples back from Mars?
That's a great question, and Ashwin actually is a perfect person to ask that, because there's a program at Jet Propulsion Laboratory that's doing exactly that.
So Ashwin, is it possible we might someday get samples back from Mars?
Yeah, we sure hope so. One of the things that we're working on here at JPL is the mission that I referred to earlier called the Mars 2020 rover. It has some really sophisticated instruments that it's bringing with it to Mars to do these kinds of investigations, to look directly for signs of life. But it also is proposed to bring samples back to Earth one day. It requires a few follow-on missions to do that, something to land a rocket on Mars.
So to sum this up faster, the idea is Mars 2020 will pick up rocks as it goes, identify where those rocks came from. Then a future mission will come and take a canister of rocks out of Mars 2020 and launch that to bring the rocks from identified locations back to Earth.
To accomplish that.
And this is actually something that kind of leads on to that. You know, we are planning to return to Mars. We have an active Mars exploration program, and one of the things we're trying to do is figure out where the best places to land next would be. So there's some questions here about how are we determining the best places to, where do we explore next on Mars?
One of the big questions is, where else are we going to find the organic carbon? And there are various environments that we understand on Earth as being good places that we can collect organic materials, that get preserved, and it's also good places for life. So for instance, a lake bed, like what we found in Gale Crater, is a perfect example. But there are others, hydrothermal systems, where hot fluids and gases coming out of the ground can provide a lot of chemicals that organisms can use. We see these in the ocean on Earth as hydrothermal vents. There are records of rocks on Mars that suggest there are ancient hydrothermal systems. So that might be another place for us to look. So right now, the larger Mars science community is talking about where it is they want to go. And these are some of the key scientific motivators for choosing sites.
Let me add to that a little bit. We have two things. We have a huge amount of data because we have very capable orbiters orbiting Mars. And on those orbiters, we have imagers that can see a few feet. We can see our rovers on the surface of Mars. We can see the rover tracks. So that's one tool we use. The other tool we use from space is spectroscopy. One thing that brought us to Gale Crater was finding minerals that were hydrated, that had water. So that was
The mineral they found was hematite. This is the same mineral that periodically gets used for jewelry.
The thing about Mars is on Earth it's very, very hard to find old rocks. And the reason is Earth is so active still. You see the Hawaii volcanoes going off, and so the landscape keeps changing. Plate tectonics it's called, it moves the continents around. On Mars, that stuff all froze out billions of years ago. So, half the surface practically is very, very, very old. So we can get at the ancient history of Mars by landing on the surface and looking at what happened early in the history of the solar system.
That's right. The modern landscape is actually a very ancient one.
Yep.
Yeah.
So we're going to go to another media question. So this will come over the audio line.
Thank you. Next question is from Mike Wall with Space.com. Your line is open.
Thank you, guys. Really appreciate your time. This is all very interesting stuff. This is probably a question for Ashwin, but if anybody else wants to jump in. But you're coming up on 6 years now on Mars, and so how do you think these results and totality of what Curiosity has found will sort of shape its legacy? And I know it's weird to talk about that when you're still going strong, but it's almost been 6 years now. So yeah.
I have no idea how they're going to answer this. I can't understand it.
And Ashwin, I hope that came through well. I believe the person's asking about how these discoveries will fit in with the legacy of the Mars Curiosity rover and your view of that. Some comments from you?
Yeah, it's a great question, and sometimes being involved so deeply in the day-to-day, sort of forget to look at the bigger picture. But as I mentioned earlier, the way I think about it is really that we have a role in this ongoing exploration of Mars that's now been going on for more than 50 years and will continue in the future as we get closer and closer to understand if life ever originated on Mars, and then eventually sending humans there and maybe even colonizing Mars one day. And the role that Curiosity was designed to play was to figure out if Mars ever was habitable. We didn't know that before Curiosity went there. We didn't know that lakes survived on Mars in this time period from 3 to 4 billion years ago, that they were surviving on Mars for up to millions of years. And we didn't know the extent that organic matter was present on Mars, could be concentrated in these environments, and would be preserved for us to study today. So those are some really big questions that the mission was specifically designed to address. And with these results, I couldn't be happier in how we've been able to meet those objectives and provide them as material for future missions to use when they're designing where to go and how to accomplish their science.
I think we just have a little bit of time left, but I think there's one more question from the media. We're going to try to sneak in, so please go ahead.
Thank you. Our next question is from Hillary Breck, Business Insider. Your line is open.
Hi, yeah, thanks for taking my question. I just wanted to ask a question about those class rates that the methane is coming from. Do you think that it's the rising summer temperatures that are warming those up, and that's how they're releasing it?
Chris, want to talk about some of the possible sources for the rising methane levels in the summer?
Yes, you asked about cleth rates. So there is cleth rates are stable on Mars. They're created through the high pressure, of course, initially. They could be a source, but we don't believe, remember, once you get under the surface by several meters and below that, you don't really have a seasonal cycle there. It's pretty constant temperature. So the cleth rates or other reservoirs might be leaking or seeping the methane continuously throughout the year. It's only when it gets to the surface, where the surface temperature has that seasonal cycle, that modulates the release of that methane into the atmosphere. I think that was your question.
Well, that's actually all the time we have. If you submitted questions via social media that we didn't get to, we're going to spend the next hours and days trying to get to as many of them as we can and answering them online. But for now, thank you so much for joining us. We were live at NASA, and have a great rest of the day. Bye.
So translation, wrong screen. Okay, so translation, something else is about to come on NASA TV, so we have to get off the air. And I have to admit, I have to get off the air too. I have a meeting to go to. This has been a great past 2 hours. This started off with today's Daily Space, an extended version bringing you all the news from the American Astronomical Society meeting in Denver. We then transitioned over to bring you coverage from NASA's press conference on the discovery that methane on Mars is seasonal, and the second discovery that there are complex organic molecules on Mars consistent with what is needed to have life. This doesn't mean there is life. This really doesn't mean there is life. But it's still tantalizing because it means life isn't eliminated. Now, if you like what you see, please give us a subscription. Thank you so much. Please give us a follow. All the follows I saw today, thank you so much. Let me give you one further shout out. Thank you, Ginny Artemis, for following. Thank you, Ace in the Base. Thank you for the bits, Keeper of Maps. Thank you, Bambino the Gray, for the follow. Thank you, Paul Person, for the follow. Thank you, Nick Saga, for the host over. Thank you, Dr. WD40, for the host over. Thank you also, Saman, for the bits. And thank you for the subscription stoners. This has been a great chat, and I am so grateful for all of you coming and bringing your amazing questions with you. We will be airing the Daily Space again tomorrow, starting at 1 p.m. Eastern, that is 10 a.m. Pacific, and 6 p.m. London. This evening we may have an episode of Learning Space. Susie is on that and probably knows more than I do. So keep an eye out on Twitter where we will be letting you know all that is new coming to you from CosmoQuest X. And please, if you have a few spare moments, go over to CosmoQuest.org and try your hand at doing science. We have a particular need for help mapping out Mars and Mercury right now, and every crater you mark helps us get a little bit closer to completing our science. If you like what you see, please consider a subscription or bits. This is a project of CosmoQuest.org, and we are brought to you by the Astronomical Society of the Pacific, a 501c3 nonprofit dedicated to putting science in your brain. We are working in collaboration with a number of other institutions, including the Planetary Science Institute and Youngstown State University. So thank you once again, and I will see you more online. Wherever you are in the world, please have a wonderful morning, evening, or afternoon, and remember, look up. Bye-bye.